All right, example number 7. Differentiate this fun function looking thingy do. I won't lie, it's somewhat diabolical. Written as a negative 4/5 power just to start you off with a quotient inside. So the function itself is a rational function. So although this is an application of the power chain rule, we're going to have to be, again, very careful on what we want to do. You have two choices. You can use the power chain rule with a quotient rule, or again, maybe challenge yourself to do a little algebra first and get that inner function to something that's a little easier to differentiate. And what do I mean by that? Well, I see a single denominator inside, so maybe you try to rewrite this as a set of functions raised to the negative 4/5 rather than a single function raised to the negative 4/5, which could be helpful. So pause the video, go ahead and do that. See if you can rewrite the inner function as a sum or difference of two functions raised to the negative 4/5. All right, so here is what we get. Again, dividing out our 8x and 8x to the third, or sorry, 8x and x to the third gives us an 8x to the negative 2. Again, that's an easy differential to find, so I'm perfectly good with doing that. And then the x to the 6 minus, x to the 6 divided by x to the third gives me x to the third, all raised to the negative 4/5. So now I have something that's a lot more manageable. You'll find after doing lots of derivatives, using the quotient rule isn't always the most fun thing to do. So rewriting this and applying the power chain rule is probably a better one. So go ahead and pause and see if you can work this out to get a simplified derivative function for y. All right, so just applying the power chain rule, we get a negative 4/5, 8x to the negative 2 minus x to the third to the negative 9/5 times the derivative of the inside, which in this case is negative 16x to the negative 3 minus 3x squared. Don't mess that one up. A lot of people just get used to adding or subtracting 1 from the numerator, and they always see the number getting smaller, but in fact, smaller than negative 2 is negative 3. So we just have to be careful of that one. If you have a x to the negative 1 right now, you are going to get yourself in trouble in this problem. All right, so the hard part is done. The rewrite and the derivative is taken. Now it's all algebra 2 from here. So we are going to take and combine these two, rewrite with a rational exponent that's not negative, and try to clean up what's inside. To do that, I think it's best to kind of consider what's going on right here. This 8 over x to the negative 2, I'm just going to rewrite that for you. So I'm going to keep my negative 4/5 right now. And I'm going to rewrite this as 8 over x squared. And then minus x to the third, but I want to get a common denominator. So I want to have something over x squared here so that I can eventually combine these. So I'm going to make this an x to the 5th over x squared. I'm going to do the same thing over here, that this is going to be a negative 16 over x to the third. I want to rewrite 3x squared with an x to the third in the denominator, so I'm going to make this a 3x to the 5th over x to the third, so that I have common denominators here that I can start combining. All right, why don't you go ahead and pause it and see if you can clean this up and get a derivative for y. Come on, I said pause it. Didn't you pause it? Pause it. Pause it. All right, so here I have written for you the next step. I realized, by the way, that I did miss my exponent over here, so I added it back in if you were getting all angry about that. But rewrote this first term as negative 4 over 5 times the function to the 9/5, and then rewrote this as a single fraction as well. From here, you're just going to be combining things and factoring. So I have limited space on my iPad to do this, so I've given you what is the simplified answer with a single denominator and rational exponents. So hopefully you can get it to this spot. If not, check your signs, check your common denominators, check all of that fun stuff. All right, so let's move on to the next one. Almost done. These ones aren't so bad in terms of their complexity, so I think these last few will go a little quicker than those first ones did. But trying to differentiate y equals 2 to the cotangent x. So again, we want to make sure that we define our f and our g properly here, that our f of x is going to equal 2 to the x, and our g of x is going to equal the cotangent of x, which means that f prime is equal to 2 to the x ln 2, and g prime, we need the derivative of cotangent, which is negative cosecant squared, and we want to put them together into an f prime of g, so 2 to the cotan x ln 2 times g prime, which is negative cosecant squared x. And that's dy dx. We want to clean this up a little bit. There's really no great way to write these when you have these kind of products of functions that all seem like they blend into each other, but I'm definitely going to pull the negative out in front and call this the opposite of 2 to the cotangent x ln 2, and I just might do this to kind of keep things separated. And I would say that that's probably a decent looking dy dx. Alright, second to last one here, example number 9. So this is another this is a composed function within a composed function. I think we all recognize that f of x can be rewritten as cosine of x cubed, which itself is a composed function, all to the second power, which now brings in the power chain rule as well. So I'm going to write this one notationally just a little bit different so you can get used to seeing some other things. We are looking for f prime of x. And to do so, I am going to apply my power rule. I'm going to say that this is 2 times cosine x cubed to the first power times d dx of cosine of x cubed, meaning that derivative, the derivative with respect to x of cosine x cubed, is going to be the chain part of the chain rule. So that's 2 cosine x cubed times the derivative of cosine x cubed. Well, the derivative of cosine x cubed is the derivative of cosine evaluated at x cubed times the derivative of x cubed. So negative sine x cubed times 3x squared, making f prime of x, the derivative that I am looking for, is going to be negative 6x squared cosine x cubed sine x cubed. Now that's an interesting one. Cosine x cubed sine x cubed. I wonder if there's an identity that relates cosine and sine of the same thing when there's a product. And I believe there is. Let me get a different color here real quick. Alright, so cosine A, cosine, oops, that's supposed to be a sine, cosine A, sine A. Anyone know the identity that relates cosine A, sine A? I believe there's one. It says that this is equal to 1/2 sine 2a. So I can rewrite this cosine x cubed sine x cubed as 1/2 sine 2x cubed. So that gives me f prime of x is equal to negative 6x squared times 1/2 sine 2x cubed. So I can simplify this all the way down to negative 3x squared sine 2x cubed. That is a nice derivative. I know it would be tricky. I'm not saying that you guys should all know the identity. I know you could look it up. Go ahead and look it up. Cosine A, sine A. But yep, that's an interesting way to get that simplified answer. Otherwise, your answer is going to come out in terms of sine and cosine. So that would be a very tricky C, even for a expert derivative taker, to figure out how you're going to use the chain rule and not have this in two variables without a Pythagorean identity to substitute in for. All right, one last one on the last page, and then we're done. Yay! All right, last one here, and I absolutely love these types of questions. And I don't know if my love of these types of questions comes from the fact that they seem to make it on the AP exam every year, or I just love when you don't have a defined function, but you need to understand the rules that govern how those functions behave when taking derivatives. So here you're given a composed function h of x, which is f of g of x, where both f and g are differentiable functions. And then you're told some information about the functions evaluated at particular values and their derivatives evaluated at different values. So you know that g of negative 1 is 2, g prime of negative 1 is 3, and f prime of 2 is equal to negative 4. And the question is, what is the value of h prime of negative 1? So to do this one, we're simply going to write our h prime equation. H prime of x is equal to f prime of g of x times g prime of x. From there, we can start doing some substitutions. We want h prime of negative 1, which is going to equal f prime of g of negative 1 times g prime of negative 1. Just going to warn you, my kids are going to walk in the house and hear me making a math video and start making fun of me. But whatever. H prime of negative 1 is going to equal f prime of g of negative 1, and g of negative 1 is 2, times g prime of negative 1, and g prime of negative 1 is 3. We see that f prime of 2 is equal to negative 4. Negative 4 times 3 is negative 12, and we have found h prime of negative 1. We did it. See you guys later. Bye.